A massive dying star and a human brain suffering from Alzheimer's both succumb to the exact same terminal disease. This is a literal mathematical system crash. Both systems collapse because they slowly accumulate heavy, dense data that they simply lack the energy to process. The culprit behind both of these massive failures is a single, unyielding element: iron. Iron is the one physical file format the universe cannot compress, rewrite, or delete without triggering a complete and violent hardware reboot. This animated graph shows the binding energy per nucleon for every element. As lighter elements fuse together, they climb this curve, releasing energy along the way. But the math hits a hard ceiling right here at iron 56, the absolute bottom of the cosmic gravity well. Fusing lighter elements keeps a star stable, but trying to fuse iron absorbs power, turning it into a massive thermal heat sink. That sudden, violent energy drain instantly crashes the star's core. The iron acts as an immutable piece of hardware that cannot be deleted, forcing the star to collapse inward under its own weight and explode. To keep reality running without constantly crashing into these heavy iron nodes, the universe manages its systems using lighter, fluid elements that act like software. Hydrogen serves as the raw carrier wave. It is the baseline, highly mobile fluid that moves unformatted data seamlessly across space. When chaotic radiation hits the system, an element like lithium acts as a transformer. It catches that raw energy and instantly splits it into two distinct parts: highly energetic, usable fuel and a protective byproduct. That byproduct is helium. It functions as an absolute zero-state coolant, wrapping around the heavier hardware in a buffer field to prevent the immense heat of cosmic friction from melting the entire system. Biological systems face a massive dilemma. To survive, they have to safely contain and utilize that heavy, unyielding iron hardware without letting it crash their delicate chemical networks. Biology solves this by weaving a programmable carbon mesh into a geometric cage, known as a porphyrin ring, locking a single iron atom securely in the center. Once isolated inside that carbon cage, iron's immense, immovable density goes from being a systemic hazard to a flawless biological tool. We can see the exact physics of the stability in a technique called Mossbauer spectroscopy, where scientists exploit iron's rigid crystalline structure to catch wireless quantum signals. Because iron locked in a lattice is exceptionally heavy, it prevents physical recoil. Fire a gamma-ray ping at it, and it absorbs the momentum without moving, emitting a perfectly clean echo. That stability is so reliable, NASA miniaturized these exact iron-based sensors and sent them to Mars to wirelessly ping the soil and analyze its history. The carbon cage neutralizes iron's destructive weight, transforming the heavy metal into a perfect causality anchor for processing local data safely. But this localized data processing has a hard limit. The human brain runs on tiny chemical millivolts, completely lacking the tera-electron volts required to break down a stray iron atom. Without an active outbound port to physically excrete excess iron, the human body locks the heavy metal away in specialized protein cages called ferritin. Over a lifetime, these biological server racks fill up, creating a critical indexing issue when they finally reach their maximum storage capacity. When that buffer overflows, the system loses containment. Rogue, unallocated iron spills directly into the bloodstream, exposing the brain's delicate neural network to raw, unyielding metallic hardware. The exact moment of biological failure happens when this free-floating iron collides with hydrogen peroxide, a natural byproduct of our cells breathing oxygen. That collision triggers the Fenton reaction. It is a literal biological rusting process, where the iron violently strips electrons from the surrounding tissue. Acting like a thermodynamic wrecking ball, this oxidative rust forces nearby proteins to misfold into chaotic, branching shapes that physically crush the neural pathways. Those tangled microscopic structures are the exact tau tangles and amyloid plaques that drive the macroscopic cognitive degradation we observe in Alzheimer's disease. We are, in every physical sense, scaled-down nuclear engines. Our ability to think, move, and survive relies entirely on our delicate carbon cages holding the line against the rusting, immutable weight of iron.